Okay, so we are live on YouTube also. Okay, so one more minute and we will start. We are live on YouTube also. Okay, so one more minute and we will start. We are live on YouTube also. Okay, so one more minute and we will start. We are live on YouTube also. Okay, so one more minute and we will start. We are live on YouTube also. Okay, so one more minute and we will start. We are live on YouTube also. Okay, so let's start. So, ladies and gentlemen, esteemed guests and fellow enthusiasts of Cosmic Frontier, I am Parth Pandya, co-founder of Zeta Gravit, and I welcome you all today to today's extraordinary event, where we embark on a journey through the realm of geodesy and astrophysics. Ladies and gentlemen, it is my utmost pleasure to stand before you as your host for this captivating voyage into the depths of scientific exploration. I welcome you all. Our first speaker, Shrishail, a PhD student at prestigious EFZ German Research Center for Geoscience Postdoc Space Satellite Geodesy, is here to enlighten us with his expertise in space and satellite geodesy exploration. His talk titled Geodesy Odyssey, Journey Through Earth's Dimension, promises to unravel the mysteries of our planet's intricate dimensions. Through his dedicated research, Shrishail invites us to witness the fascinating interplay between satellite, space, and Earth's surface, offering us a profound understanding of our world's dynamic nature. Following Shrishail's enlightening disclosure, we will be graced by the presence of Gaurav, a distinguished PhD graduate from IIT whose passion for astrophysics knows no bounds. With a remarkable background in high-energy transient and a proud member of LIGO, Gaurav's talk, Astrophysics Adventures, journeying through high-energy transient, LIGO India, Daksha Sat, and more, promise to transport us beyond the confines of our terrestrial existence. For his insight into the enigmatic realm of astrophysical phenomena, we will be blessed by the presence of Gaurav as we embark on this exhilarating odyssey to the frontiers of geodesy and astrophysics. Let us open our mind to the wonders that await us. And a proud member of LIGO, let us delve into the depths of geodesy. So, Shrishail sir, am I audible? Yes. Beyond the confines of our terrestrial existence. How are you into the enigmatic realm of astrophysical phenomena? We will be blessed by the presence of Gaurav as we embark on this exhilarating odyssey to the frontiers of geodesy. So, without wasting further time, let's get diving into the high-energy transient and a proud member of LIGO. Let us founding from Mars to the astronomic love of PDU to pursuing PhD in space satellite geodesy from EFZ. Yes, beyond the confines of our terrestrial. So, how are you into the enigmatic realm of astrophysical phenomena? We will be blessed by the presence of Gaurav as we embark on this exhilarating odyssey to the frontiers of geodesy. So, without wasting further time, let's get diving into the high-energy transient and a proud member of LIGO. Let us you are not audible. Of PDU to pursuing PhD in space satellite geodesy from EFZ.
I'm sorry, there was an internet connection.
So, how are you? Tell us about your journey from physical phenomena to PhD in space satellite geodesy.
Yeah, that in brief.
So, without wasting further time, let's get diving into the one topic.
So, I'm not sure if I can go
Let's
through this journey,
you are
but
not
I'll
able
try
to
my best. So, I started my engineering in 2012, and I was always interested in astronomy. We co-founded astronomic club, which we gave the name Brahman, which is universe in Sanskrit. And that's how the journey for Brahman began. And we started conducting several workshops, including telescoping workshops, some talks, some seminars in our club. And on other hand, I was also a part of a we co-founded group which was called Rat Club Home, which we gave the name, which was started by Dr. Ananda Mohan from Mumbai. The objective was to search for several galaxies with an workshops. I was a member for this association for roughly 2 years, and as a part of my engineering program, we have to do some workshops, including telescoping, which is compulsory. So I decided why not combine engineering and astronomy for this internship, and for that I joined as a co-founded Indian group, Astrophysics, where I was working, which was on a small part in this telescope project. And I was there for 6 weeks. The objective was to started conducting for several working on galaxies with and workshops, aberrations which occur in the mirrors, specifically 2 years, adaptive optics, and how do we try to solve it, and workshops, and aberrations which occur. Meanwhile, I also presented these works specifically 2 years, adaptive optics, and the Astronomical Society of workshops in the yearly meetings. And after finishing my bachelor's, specifically 2 years, I also started working in the Astronomical Society intern after my graduation. The plan was to work there for 1 year, specifically 2 years. I also started working intern, but fortunately, or I don't know, unfortunately, I got accepted to do my master's in space engineering program from Technical University of Berlin, and which I started my studies in the summer semester of 2017. And I don't know, there were some courses in Geodesy, some introduction courses, and some specific courses. And this got me quite interested in this particular field, which I started my studies where we studied the Earth, and somehow I got an opportunity to work. There was a nice observer at the satellite laser ranging station at GFZ, which is German Center for Geosciences in Potsdam. Potsdam is like a satellite, let's say it's a satellite town with Berlin. It's like Ahmedabad, Gandhi. Opportunity to work there. Nice observer at the station. Then I worked there for 1 year, 1 winter and 1 summer, and then I continued over there to do my master's in space, and but I did not do it with SLR, the satellite laser ranging, because they mostly did observations, and they did quite little regarding the analysis and further processing. So I changed slightly my field. So instead of doing an SLR, I did it in VLBI, because they mostly very long baseline interferometry, but instead for astronomy, we use it for geodesy analysis. So I did my master's thesis over there, and so I did afterwards, after finishing my master's, a couple of 3 or 4 months afterwards, COVID hit, and our PhD project got delayed. So meanwhile, until this main project got approved, I was working over there for 18 months afterwards in Geodesy for climate, and At the end of 2021, I joined a new project at our institute, which was called as Next GNSS for GWAS. So here the entire setup is simulation-based studies, and we focus on the next generation Galileo satellites. Galileo satellites are basically the navigation satellites or constellations by European Union's ESA. It's similar to GPS from USA, NASA, or GLONASS from Russia. And India also has Navik, for example. So I work on this with a project partner, and we'd like to study that how these new satellites would help us gain more accuracy and precision in the measurement of the Earth. So yeah.
So your journey is truly inspiring for many undergraduate space enthusiasts like fellow space nerd, including me. Now, tell us little bit about geodesy in general and how like space or satellite geodesy is different.
So for a basic explanation of geodesy, it's the measurement of Earth, and we know that we need to measure the Earth for various purposes. For example, navigation. So, for example, if you want to go from, let's say, Ahmedabad to Delhi, how do you know to go to Delhi? You need some direction, some reference points, and the distance. You need at least some accurate measurements. Otherwise, instead of reaching to Delhi, you might reach to, let's say, Kolkata or Chennai. So you need some reference points and some measurement, which we base our journey on, and geodesy does that. And there are many applications for geodesy. I mean, we use it for navigation, for surveying, for mapping. How do we map our mountains, our Himalayas, Alps? There are so many mountains. How do we know their specific heights? And we also need geodesy for the earthquake monitoring, because earthquake leads to shift in the crust, the Earth's crust, and this might lead to maybe, let's say, more than a meter. So let's say that there are several houses in a society, and your house is one of them, and we experience an earthquake. And let's assume that there are no fatalities, and the crust shifts, and somehow your plot of your land is shrunk because of the change in the crust, and your neighbor gets more portion of the land. So how do you tell which is yours, which is not yours? So for this, we need geodesy to know exactly where your point is. And furthermore, we need geodesy for satellite orbit determination. So as we know that we are moving to the space age, and there are so many satellites in low Earth orbit, in medium Earth orbit. But how do you know that this satellite is on its orbit? So it's like it's like you're moving in a car, and how do you know from at a long distance that your car is going in the same lane? So similar, it's with satellite. So more precisely we know the position of the satellite, the more benefits we get. And also we need climatic studies. How do we know the sea level is rising? We need to have a reference point. If there is no reference point, we would never know the sea level is rising or it's not rising, if the land mass is shifting or not shifting. And geodesy exactly provides us this reference. And how do we measure this thing? there are several techniques to do that. But before that, I will just briefly mention that it's just not the measurement of some reference points, but it's the measurement of the shape of the Earth, which changes over time. It's time variable. We measure the gravity field of the Earth because the gravity field of the Earth changes because somewhere we have a huge amount of mass, somewhere we do not have that amount of mass. For example, in the mountainous regions such as Himalayas, Alps, since there is large concentration of mass in a small area, it has slightly more gravity compared to other regions. So we also need to know that precisely because that affects our measurements. And how is Earth with respect to the other objects, other celestial objects? How is our spatial orientation in the space? How is our Earth rotation? Our position with respect to other celestial objects. These are all crucial, and geodesy does that. Yeah, I think.
It's indeed an interesting topic to study about. Like, really, it's interesting. So, sir,
Yes.
now tell us how can we study climate change with the help of satellite geodesy? Like I heard or read somewhere that there's any group who does that. So, like, tell us something about how can we study climate change with the help of satellite geodesy.
Yeah, so I can give you an example. Uh, so there are many climatic phenomena which are going on. So, for example, we have the ice, the loss of ice sheets in North Pole and also in the Antarctica. So, as we know that if the ice melts, where does this water go? It goes into the seas, and the seas lead to high sea level rises in the coastal regions around the world. And this exact shift of mass would change the rotation of the Earth. So, as you know, the conservation of angular momentum. You I think know the explanation where a ballet dancer who spins quite slowly at her or his axis slowly if their hands are away from their rotating axis, and as soon as they bring their hands close to their rotating axis, the speed, the angular velocity increases. The similar thing is with the Earth. So any change in the masses around the Earth, it reflects in the Earth's rotation, the polar motion of the Earth, and this can be seen. And I also did a similar study 2 years ago, and we also published some interesting results about this. So there's a phenomena which is called as El Nino phenomena. I think most of you might have heard about this. This occurs in Pacific Ocean. And in this particular phenomena, huge amount of water vapor and seawater is transported from one position to another position. The first position is the Central Pacific, and the end position is the west coast of South America because of differences in the heat or temperature in the sea level. Temperature in the sea. So this particular phenomena can be seen in the Earth's rotation. So it slows down our Earth's rotation by it's in milliseconds. It's quite negligible change, but this change is enough for us to know that these things affect globally, and this particular changes need to be done in our calculations so that our other things are not affected. And there are several climatic phenomena which happen around the world, which help us. We can monitor that. And another interesting part with this is there was satellites launched a few years ago, which is called Grace and Grace Follow On, and these satellites help us determine the changes happening in our gravity field around the Earth. And it can, point to be noted that it can only measure the changes in the gravity field. So, for example, that there was recently a study published and around New Delhi area that, or in Punjab region, and this study showed that the groundwater level in the northern part of India was steadily going down, and it has almost completely depleted. And this change of water table going down can be easily seen in this from this satellite, which also gives us an idea that how we are using our resources judiciously or not. And with this, we can monitor our country's resources as well. Yeah.
Yes, so thank you for this insightful perspective. It's truly remarkable how satellite technology enables us to monitor and understand the intricate dynamics of our planet's climate system. Now, I did
Yes.
love to delve deeper into your experience as a night observer at Satellite Ranging Station SLR GFZ. Could you share with us some highlights or
Sure.
memorable moments from your time there?
Sure, I can certainly do that. Before that, I will explain what an SLR station does. So, SLR stands for Satellite Laser Ranging. So, from the abbreviation, you can understand what it might do. So, we know that we have satellites revolving around the Earth, but how do we know its orbit? So what we do is, using this SLR station, we send a laser beam in terms of pulses, whose frequency is roughly 2000 hertz. And the satellites are equipped with a retro reflector on its nadir pointing side. So the nadir pointing side of the satellite is the side which points directly towards the Earth. And we get some prior information about the satellite's basic orbit. So we know where the satellite is going to be using the TLE data from NASA's website and other websites. And we then start searching for this particular satellite. And as soon as we find the satellite, and this particular laser reflects off this retro reflector, and the retro reflector is built as such that it sends back the light back to the same position. But let's not talk in terms of light, let's talk in terms of photons. So for every millions of photons which are sent from Earth, maybe we get 2 or 3 photons back. And this SLR station at Potsdam has 2 set of telescopes. So one telescope transmits the laser, and the another telescope receives this reflected photon of the satellite. And it's an engineering marvel, if I must say, that imagine you're sending the laser beam maybe 400 to maybe 20,000 kilometers away, and you are getting this photon back to the Earth. So in most of the geodetic techniques, the main thing which we measure is time. So we know when the photon leaves this transmitting telescope, and then we know when do we get back the photon. So we know the time, we know the, how do I say, the time which it gets back to the Earth, and we know the speed of light. So we get the distance of the satellite with respect to the SLR station, and there is a large network of SLR station spread across the world, which do their own part whenever this particular satellite passes over them. And this is, let's say, this is somehow you do your work. I mean, this is how SLR station works in principle. Uh, so this helps us in understanding the orbit of the satellite. So me working as a night observer over there, I worked there for 1 year, and it was initially a bit challenging for me to work over there, but also quite interesting. And I learned the trade maybe in a month, and and I think I started my work in the month of September, which is beginning of autumn. And also the thing is, since I am situated in north part of Germany, the latitude is almost 51 degrees north. So there is extreme daylight. The length of daylight varies with respect to, I mean, in winter and summer. In winter, we have almost 18 hours of daylight and in winter, we have 18 hours of night and 6 to 7 hours of daylight, and it's vice versa in summer. And in winter, it's rather easy to get more information from the satellite because it's night most of the time, and the sun is not there to interfere with your results, because sun also has a lot of gives out a lot of photons, and this we get this as a noise in our system, and then we need to do extra processing to differentiate the receiving photons from the satellite from sun. So I was able to learn this quite easily in autumn. However, since it's a laser, it's an optical domain. In whenever there are clouds, we cannot observe the satellites because they physically block the lasers. And in winters, we also have some cloudy days, so we are not able to do the SLR work. I mean, the satellite ranging work during this particular time. And I was for this particular time, I used to work 40 hours a month, which roughly translates into 10 hours a month, 10 hours a week. And I would do 2 nights or 1 night, and and I would do whenever there were a lot of satellites visible from our location. So usually evening time and morning times were where we had a lot of satellites. So I used to mostly cover up these shifts to track as much satellites as I can, because if I'm doing there, I should do something. I should not just sit there and get paid for doing nothing. So we had to optimize like that. I mean, now the station is quite automized, but back then the automation was not completed. So we had to go to the station and do it. And I think, Parth, I have also sent you a picture of the SLR station which I took, so you could also show in your YouTube so that people get more context about what I'm saying.
Yes, sir. Like we have already displayed on our YouTube.
Okay, cool. Thanks. And I worked there for 1 year, and I think the most memorable was when I actually took the time lapse of this particular working of this SLR station, and it was in winter, and it was freezing cold, let's say -8 degrees, and somehow my GoPro survived for 8 hours in the night, and I was able to take a nice time lapse of this station, and the photo which Path is showing is a snapshot of this time lapse video. Yeah, I think. Yeah.
Sir, thank you for providing such a detailed insight into your role. So, like as
Thank
you
you.
said, like now station is a little bit automated. So, like back then, what were technical operations that you were supposed to perform?
So, um, my job was to, I can just give an example of one evening. So, if there are maybe, let's say, 20 satellites visible in a span of 2 hours, so I would particularly have a list which is called the priority list. So, there were some satellites which we had to give high priority because they were quite important for geodesy. And there was some space debris which we used to also track, and they used to get some medium to low priority. And according to that, I used to make up my plan that okay, I will track this satellite, and then next, and then next, and so on. So that was the basic plan for the evening. And after I get enough information about the satellite, I would then switch to another satellite. And one thing also is to be noted that depending on the attitude of the satellite, also I had to make some decisions. So there were some low Earth orbiting satellites, which usually they are they pass you like within 5 to 7 minutes. I mean, if you have seen ISS, so I think the sky time which you can see is 7 minutes, I guess so. So they used to get high priority. And there were some GNSS satellites, so the navigation satellites, for example, GPS and Galileo, etc. So they used to fly 29,000 kilometers up in the sky, which comes in medium Earth orbit. And typically, you can see them uh, 12 to 14 hours at a stretch. So usually, I will not track them when I used to track these low Earth orbiting satellites, because I know even after 2 hours, this high flying satellites will still be visible. And then I used to observe them. And another thing which I had to look out is for clouds. So that also played an important factor in deciding my plan. So even if I had an important satellite, which a high priority satellite which I wanted to track, I could not do it probably because there is some cloud in that particular area of the sky, and I had to skip it. And then the priority will go to another satellite. And the station was equipped with a rain sensor. So if the rain starts, the dome will close automatically because you don't want water to get into your optics and your instruments, which will eventually get spoiled. So this was one thing to look at. And also we had a system where it was connected to the air traffic, and we were not legally allowed to uh, you know throw lasers at the airplanes. So if there is an airplane in the vicinity, we would have to shut down our operations till the plane passes. And the main challenge was with this small flying aircrafts. So sometimes they do not show up in the radar. So we had an outside camera, and we had to have an eye on that if we can see them. And if we see them visually, after visual confirmation, we used to pause our tracking. And another thing was with the sun. If we are tracking in the day, we had to be very careful that we do not track satellites around in and around the sun's area, because you know the sun's intensity might kill our instruments. And there were some of the challenges which we encountered, especially in summer. So the telescope is located in a tower, and in summer the temperatures here one time reached 39 degrees in 2018, and it was there for a week, I guess. And because of these high temperatures, the station had tilted by few millimeters. And this shift we could observe in our observations. So to prevent this, or to minimize the heat effect, we covered the stations, internal pillars with aluminium foils, and some sheet of paper which would maintain this temperature. This was something interesting. I never thought that the slight tilt in the station would affect so drastically in our observations. As I have said before, that in geodesy, the reference point really matters, and you have to be sure what is the accuracy and the precision of this reference point, because we do all our measurements with respect to this reference point. And what if this reference point is unreliable? Then all of our calculations are then wrong. So that's why we have to be very careful in this particular regard. Yeah.
Yeah, that was again like a lot of information, but like it was interesting. So,
I hope
how
so.
can
Yeah.
individuals, yeah. So, how can individuals interested in geodesy can pursue education, and like what are career opportunities available in this field?
So you want to know how one can pursue geodesy and what are the career aspects after you finish uh, your education in geodesy?
Yes.
Okay, so I think my path was very unconventional, and most of the people in the West and in Japan, in Australia, they have bachelor and master courses in geodesy, and then they continue with PhD. And geodesy does not comprise only of space or satellite geodesy, but it has many other faculties such as geoinformatics, remote sensing, and computer vision, and surveying, and mapping, and cartography, and there are many. And in India, currently, I don't think there is an institute which gives bachelor's on this particular degree. Recently, we did not even have geodesy programs, but now we do have geodesy programs in the National Center of Geodesy, which is at IIT Kanpur. I think they have a master's program now, and I think they also have some PhD opportunities and etc. Because India plans to have two SLR stations in one in Mount Abu in Rajasthan, and one in Pon Moody, which is in Kerala. And India do plans to have VLBI stations, which is this very baseline interferometry for geodesy stations, uh, somewhere in north part of the India country. In principle, we do have VLBI stations in India, the GMRT, which is the most famous one in the Y configuration. But these telescopes are optimized for astrometry and astronomy and not for geodesy. And we have three GNSS stations. So one is in Lucknow and another is in Bangalore. And India is certainly late for this geodesy, but I think India in the next coming years will grow tremendously in this particular field. And we also have a strong space sector here. So this will obviously complement. And even if you don't have a master's in maybe in geodesy, maybe you could also do some diploma courses abroad, or do a second master's in this particular field, or you can also do space engineering like what I did. And we also had courses about geodesy. Of course, the learning curve for me is much bigger because I had to learn many things about geodesy which I did not learn, but this was also an interesting part. And after you have an education in this particular field, you can of course work in the space sector, and the National Center for Geodesy in India. Maybe we'll have many more centers such as in India. You can work abroad. In Europe, there's a lot of geodesists here. In US, you can also work. And and this will be quite important in the near future, because now it has I don't know how it is called, but there is a wing for the United Nations. So to have a global, consistent terrestrial reference frame, it is a thing now, and it is quite important that we have a single terrestrial reference frame across our globe, so that we can monitor our borders, our climatic changes, the movements in the country, and then there are several advantages of having this consistent terrestrial reference frame. So the things are moving quite fast as of now, and I think in near future there will be nice and good opportunities in this particular field. Yeah, I think
Thank
it
you
should be.
for sharing, sir. So, sir, what
Yeah.
inspired you to pursue a career in geodesy, and what is advice would you like to give to your juniors?
Uh, what sparked interest for me in geodesy? Maybe it was due to, since I was always interested in astronomy, and because when I attended few lectures of geodesy, I think I have told you this technique called VLBI, very long baseline interferometry. So here also we look at the quasars, uh, and which are considered as the radio sources, and these objects are quite far away from our Earth, and we use this particular radio sources. We have a catalog, and we use this as a reference point, and we measure the movements in the Earth with respect to this particular reference point. And since I was already interested in this part of the uh, story, I got into it, and even though I started with this, I mean, I was motivated because of this, and this helped me get an entry in to take an entry in geodesy, and then I got quite interested that I have because I had never heard about geodesy my entire life until I did my started doing my masters, and I realized that how important is this for the world and how interesting it can get. You can understand our Earth's dynamics with in this field, and yeah, then I just started with this field, and I just got interested, and then the rest is history. And I mean, the advice which I would like to give is like, uh, no matter what you plan, how you plan, you will never know that what future lies for you. I mean, I know that I was interested in these things. I explored many options. Some I liked, some I did not like, and I just went with the flow. And you should also be quite aware of the opportunities around you, because sometimes you are interested in a field so much, but there is no money in those fields. There's quite little money. So you also have to be quite practical, and you have to also think about these aspects along with your interest. And if you can combine your interest with such a field which also has money, because science nowadays cannot proceed without funding. So then that's quite a golden chance. Yeah, this is one I would like to tell to the listeners.
Okay, sir. So, thank you once again for sharing your valuable insights and experience.
Thank
We
you.
are grateful for your contribution to the field of geodesy and for your commitment to pushing the boundaries of knowledge and exploration. Thank you once again. We
Thank you,
look
Parth.
forward to hearing more about your groundbreaking research and discoveries in the future. So now I
Sure.
think we can move forward to our Q&A session. So like if you have any questions, you can just put it in comments or like request for speak. I will allow you.
Again, I will try to answer of best of my ability.
Thank you, sir. Sure. So there's one question from one of our teammates, which
Okay.
is like, can you discuss the role of geodesy in supporting infrastructure projects or urban planning and land surveying?
Uh, yeah, I can try to answer that. So, uh, I think urban planning requires some precise measurements, and mm, I think these questions mostly come in the field of surveying and mapping, and probably not so much in space geodesy.
Okay, sir. So, like, once
Yeah,
again, thank you for
yeah, thank you.
sharing. So, now we will have a little 10-minute breaks, and like in between, we will have one fun quiz. So, handing over to Datta,
Yeah.
he will host
Thank you,
the
Paul.
quiz session. Thank you, sir.
Yeah, thank you all.
Datta, can you hear me?
Yeah, yeah, I can hear you. So let's start the quiz. I hope you can see the screen on YouTube questions. Meanwhile, I will also narrating the questions for you. So here comes the first question. What term describes the bending of light rays due to the gravitational attraction famously predicted by the Einstein's theory of general relativity? So your options are gravitational waves, gravitational force, gravitational lensing, and none of these. So any of you guys know the answer, you can speak or type in the comments. Anyone? So I guess no one answered it. So the answer for the question is gravitational lensing. So next question. What's the name of the closest star to the Earth? I guess this is the easy one. Anyone? I repeat. What is the name of the closest star to the Earth? Your options are Alpha Centauri, Proxima Centauri, Sirius, and Betelgeuse. So answer for it is Proxima Centauri. I guess we can start the session. Path, over to you.
Okay, so I guess uh, let's wait for 2 minutes, then we will start. Hello, Gaurav sir. Am I audible? Hello, Gaurav sir. Okay, so seems like there is some issue with internet of Gaurav sir. So before moving forward to our next talk, a big shout out to Damodar, Ghosh, Atharva for giving correct answers. So well done, guys. Thank you for participating. Mm, let's wait till uh, technical issue got clear. Hello, Gaurav sir. Am I audible? Okay, so guys, there was some technical issues. Gaurav sir is joining in few minutes. And once again, I am grateful for all of you for joining. Especially you are enjoying the discussion session. Like you can also ask questions in chat. Mm. Yes, sir. We are able to hear
Finally.
you. So I
Thank you
hope.
so much for waiting,
Yeah,
and
yeah.
I'm really sorry for the inconvenience. I was not able to join through my laptop for some reason, so I'm joining through my phone. And I hope this is good.
Yeah, yeah. So no issues. Thank you, sir, for joining. Without wasting more time, let's start our discussion session. So let's start with your journey. Tell us about your journey. Like, how did you get into Star Labs? Then, like, you are now part of LIGO, and you have also worked on astrosat data, and like you are also building Daksha Sat. So tell us something about like your journey.
Uh, yeah, I'll do that. By the way, hi everyone. I'm Gaurav. I'm a fifth year PhD student at IIT Bombay, and and like Pranav said, I'm a part of the space technology and astrophysics research lab at IIT Bombay, where I've been working on astrosat, LIGO, and I'm involved in a team where we are building this new satellite called Daksha. Um, and coming to the question that he asked, Pranav asked, and so I got introduced to astronomy back in 2015 when I was trying to uh, study for JE Advanced, and I was introduced to this one exam called INAO, Indian National Astronomy Olympiad, is I believe the full form of that, and I got selected for that, and that's how I found out about astronomy, and that was my first introduction. Through that, I I initially I had a small hesitation to really look towards the sky and to look at different parts of the constellations and to make different shapes in the sky just to um, associate or disassociate myself from astrology. But when I actually appeared for this exam and found out that a lot of math and a lot of physics to explain everything that is out there, that's how I really got interested in all of this. And a few months later, I found myself in IIT Bombay, and I saw that the institute IIT Bombay had a fantastic astronomic club called Kritika, and I I did not really look uh, anywhere else. I just enrolled myself in that club and I started attending all of the sessions. Got myself hooked to everything that is about astronomy, and I just uh, explored as much as I can in my first year. And as as many of you would probably associate uh, the the best part about astronomy is that it is quite intuitive, and the entry slab to anything that you want to do in astro is pretty low, if you want to understand something. So that's how I got hooked to the entire to all of the different topics in astro. And I found myself in my third year. I was a part. I did my mechanical engineering from IIT Bombay. So in my third year, I found myself working with Professor Varun Bhalerao here, and since then I've been working with him on all different projects that Pranav mentioned. For example, AstroSat, LIGO, Daksha, and many more. That was my brief introduction to Astro. And with time, the sort of fairy tale just kept on becoming better, and which is why I then enrolled myself for a PhD program as well here again at IIT Bombay. I just continued in the same institute, and after that, I have been since then working on a bunch of other projects, and I'm in my final year right now. So that's basically that. If Pranav, that's what you wanted me to talk about.
So thank you for sharing your remarkable journey with us. It's truly inspiring to hear how your passion for space and technology has propelled you on this extraordinary adventure. Now, turning to your question about the counterparts of gravitational wave, could you shed some light on what they are and how they relate to the phenomena of gravitational waves?
Yeah, that's one of the things that I primarily work on. So, for example, we have I I don't know if folks here have heard of black holes and neutron stars. I'm pretty sure they have. About different gravitational waves, and even Shrishail talked about some of those parts. We have uh, these very heavy objects in the universe called black holes and neutron stars. But how are they actually formed out there? These are formed when your normal stellar mass stars, which for example, sun is one of them, and you have several such stars out there which are more massive, lesser massive than sun in terms of their mass. And uh, when their natural life cycle ends, when you have their when their fuel at the core of these stars, they sort of they end up consuming. So what we usually see at the end of the life cycles of these stars is one phenomena called supernova. And I'm again sure many people here must have heard about this phenomena. Now, at the end of the supernova, what really happens is that depending on the size of the original star that you had, you either get a white dwarf, which is a remnant, which does not have any nuclear reactions going on at the core of that particular object, and it is basically a very hot object that is just cooling down because of thermal radiation. If you have a slightly by the way, yeah, our sun is one of the lower mass stars, and that is why it is likely going to end up becoming a white dwarf. But for stars that are more massive than these, what you usually end up turning into is something called as neutron stars. These are stars that are rich in neutrons, as you would expect by the name of it, and they are so massive, but very very small in size. So, for example, their masses are higher than the sun as of now. So, the mass of sun before the explosion, which is what we call as one solar mass, if you compress all of that into a size of 10 kilometers or so, that is the size of a neutron star. Now you can imagine that the density of these stars would be immense, right? So you talk about neutron stars, the densities of these objects are huge, and then the geeks out there would also be able to extrapolate that information that I just gave you, and you would be able to make out that the gravity of these objects would be also huge, as your gravity is inversely proportional to the size of the object that you have. Now, if you want to look at the gravity of any object, you usually think about the escape velocities, right? So, for example, the escape velocity of Earth is close to 11 or so kilometer per second. The escape velocities of neutron stars is also very huge, as you can imagine. I would leave that as an exercise for people who are just interested here to find out. But that's not where the universe stops itself. You also go to even more massive stars than the ones that I just talked about, and these are the stars that then form your black holes. And these black holes, as the word again tells you, uh, are literally black. So they don't emit any light. What does that mean? That they don't let any light escape its gravity, and which means that its escape velocity is much higher than the speed of light. And you can imagine that you can do all sorts of calculations and so on to find out different properties of these black holes and neutron stars and so on. But the one key thing that we are interested in today, and in my work, in what we do at IIT Bombay, is that when you have two of such compact objects, why compact? Because they are very small in diameter, just 10 kilometers for a solar mass star. You would, if you take instead of one, if you take two such stars and they are rotating around each other, because of the loss, because they are so compact, they they sort of tweak your space-time fabric, as they call. And if you imagine two rocks going, if you imagine two rocks put on a cloth of fabric, just take your normal bed sheet at your home, and you put two very massive or heavy objects on top of it, you will see that they'll slowly start going around each other if you throw them in correct direction. And they will also launch these waves in the fabric that you're holding. These are called the gravitational waves, and these are the waves that were predicted by Einstein almost more than 100 years back in his theory of relativity in 1915. Now, when these gravitational waves are emitted, the neutron stars or the black holes, they slowly but steadily, they keep coming closer to each other. And when you come very close, they'll just merge. And this is the merger of neutron stars or merger of black holes that is seen by all of the gravitational wave detectors out there. So, for example, if you have heard of the LIGO detector, which is based on the laser interferometry, they detect these gravitational waves that are launched in these mergers. But for us, for astronomers, we typically associate anything and everything that has to do with photons. So one then would ask that where are these photons coming from? So the idea there is that when you have two neutron stars going around each other and merging and then exploding, there is a very bright jet that is launched. And this jet interacts within itself, and it produces extremely bright X-rays. This explosion that I'm talking about is called a gamma ray burst, and it is the brightest explosion in the universe, which emits about 10 to power 55 arcs per second sort of energy. Now that number that I just said may not make a lot of sense. So for comparison, the number that I just said was 10 to power 55 is the amount of energy released. And for comparison, the amount of energy released in the atomic bomb was about 10 to power 21. So if you launch 10 to power 34 of these atomic bombs that was dropped at Hiroshima, you would get something like this. So these gamma ray bursts are brighter than the galaxies that these neutron stars are sitting in. So when we talk about the electromagnetic counterparts to gravitational waves, these are the counterparts to gravitational waves that I'm talking about. So gravitational waves launched by the neutron star mergers, and the electromagnetic counterpart is the electromagnetic wave, which are the photons that reach you when these X-rays are launched, and they are detected by the X-ray satellites out there. There is one more thing that happens after this, is that when these jets that I talked about, they go and ram into your interstellar medium, and this phenomena causes a lot of radiation to be emitted as well. And this is captured by a lot of optical telescopes, a lot of radio telescopes, as well as some X-ray telescopes, which are a lot more sensitive. But this is called the afterglow, the glowing that happens after very much after your initial burst of photons. So all of this comprises into this one field called electromagnetic counterparts to gravitational wave mergers. And this is an exciting field which we call as multi-messenger astronomy, because a single event is associated with multiple messengers, and these multiple messengers are bringing in information to you, and each of these messengers tell you a lot more and a lot more different about these sources that are emitting these multi messengers. So this is an exciting field that has been recently very hot in astronomy since about a decade or so. all majorly thanks to some of these recent developments in the field of gravitational waves. But I hope that was a brief intro to EMGW and all the related things out there.
Yeah, thank you for providing such a comprehensive explanation of gravitational waves and their counterparts. It's truly fascinating to learn about the multi-messenger approach in astrophysical research and how it enhances our understanding of the universe. Now, could you please explain to our audience the procedure involved in looking for gamma ray burst?
Yeah. So the procedure in order to detect these gamma ray bursts uh, is that, like I said, you don't know where these gamma ray bursts are going to happen. You don't know where these uh, neutron stars or black holes are going to merge, and they are going to create these extremely bright explosions. So what you do is you build satellites and detectors and telescopes that can look everywhere as much as possible. So there are two ways of detecting these GRBs. One is by building satellites that can detect the initial burst of photons, which is the actual GRB. And the other is to actually build telescopes that are sensitive enough to detect the afterglows that I talked about. Uh, Now, let me take a minute to explain what I just said, because part of it is very the, both parts of it have uh, a lot of challenges that we have to overcome in order to detect these loud explosions. When we say loud explosions, these are the loudest things out there in the universe, loudest or the brightest, but they are so far away that when you actually see the photon flux that reaches your telescopes here on Earth, it is extremely faint, as one would expect it to be. Now here, like I said, if you want to detect these GRBs, which happen within a fraction of second after your merger happens, you would have to devise and design certain satellites in a way that they will be able to detect these GRBs. But since you don't know where to look for, you'll have to create satellites that can look everywhere. The downside to that is that you lose out on the sensitivity. So, for example, think of it this way: using a binocular, you can look for a very small part of the sky, but you can look for quite far away, right? So your sensitivity increases, but your field of view is very small. But just using your eyes, you can look at a much wider part of the sky or your life, uh, but you won't be as sensitive as your binoculars are. So if you want to detect these GRBs, you would what we have done is that over several decades now, we have astronomers. When I say I'm just talking about the field and the astronomers and their hard work over several decades. They have designed and developed X-ray detectors that have been launched in space, and these can then detect these extremely faint X-rays coming from these gamma ray bursts. Now, these X-ray detectors are the same ones when you go to a doctor and you ask for an X-ray. We have taken those same X-ray detectors in one of our own satellites called astrosat. It was launched by ISRO in 2015, and it has one payload called cadmium zinc telluride imager, and it is a fantastic instrument out there which has been detecting Pranav, it would be worth it to just inform the YouTube folks about the crash because they are saying that the audio is not there.
Yeah, so sorry for inconvenience, guys. But like unintentionally, our that uh, XSpace got crashed. So like we have like scheduled one recently. So we will resume in 5 minutes. Hello. So like let's start. Like people will join gradually. So like you can continue, Gaurav.
Yeah, so the question was how do we look for GRBs, and I was just mentioning that we design satellites that can go out in space and look for these very faint X-rays because X-rays are blocked by your atmosphere, so you can't really deploy your detectors on ground. You have to send out them using your satellites. And we have our own satellite called Astrosat, launched by ISRO in 2015, which has been working fantastically since its launch. And we have detected over 600 GRBs, or these gamma ray bursts, which are the explosions that I have been talking about. And they are the ones that I have been studying over the course of my PhD. Now, just a small caveat or a side note for all of you is that all of the gold that you have in your home, in the world that we have on Earth right now, is all made in these extreme exotic explosions called uh, kilonovae, which are the ones that are formed when you have these neutron stars merger. Now, uh, next time when you look at the gold that you see in person, that none of that was ever formed in our sun or on Earth. It was formed when neutron stars collided, they merged, and then exploded. So this is how this is one of the cool things that we are able to study is that all the heavy elements. It was before 2017, a few years back, it was still an open question how and where these are formed. And through the observations of these GRBs, we were able to, and that were associated with a gravitational wave merger, we were able to understand where all of the universe's gold and heavy elements come from. So when we look for these GRBs, we essentially design detectors that can look everywhere, and that has been our goal since a long time. So either you can design a very sensitive telescope that can look at a very small fraction of the sky, or you can design slightly lesser sensitive telescope, but you will be able to look at a larger fraction of sky. So that answers what was asked to me by Parth, I believe.
Thank you for sharing such a detailed explanation of how astronomers search for gamma ray bursts. It's fascinating to learn about that sophisticated instruments and technique involved in this process. Now, shifting gears a little bit, could you please tell our audience in brief about Daksha Sat? What is its purpose and how does it contribute to the space exploration and research?
Yeah, so that's a great segue into the question that you just asked. So, just continuing on what I was saying before in the previous question, we at as a continuation of the activities that we have been doing. So, for example, astrosat CZTI is the instrument that I've been talking about. Um, when this 2017 event happened, I spoke in very brief about it. So in 2017, there was a neutron star merger that happened, that was detected, from which gravitational waves were emitted, and they were detected by the LIGO detectors that are functioning in US at Hanford and Livingston. They detected these gravitational waves, and within a couple of seconds of this merger, gravitational waves reaching us, we also detected a GRB coming from the same source. Now, when this particular event happened, Astrosat unfortunately was hiding behind Earth. What does that mean? That's just what we refer to in our day-to-day life. But what it actually means is that when you are looking from Astrosat's point of view, the source which emitted this GRB was behind the Earth. So we did not receive any X-rays from it because X-rays can't pass through the Earth. Now, the next thing is that if this particular source was even 20 or 30% fainter, or had it been just 10, a few times farther away, then it would have been missed by all the satellites out there right now. So there wouldn't have been any information of any GRB going off. And the last thing is that in order to study these GRBs, you not just need an X-ray detector, you need a wide, lots of X-ray detectors, lots of different types of X-ray detectors in order to get a good bandwidth of the energies that you are trying to study. So, for example, the detectors that we use, they go from this energy range called kilo electron volt. So 20 keV to 200 keV is the CZTI detector. But we want to study these GRBs at much wider bandwidth. So you would want to design a satellite in future, if we get the chance, uh, which can achieve all these three things that I pointed out, which is that you would not want to miss any of the events just hiding behind Earth. You wouldn't want to miss any event because you are not sensitive. And you would want to study these events when they go off as much as possible by collecting as many photons as you can. So, to achieve all three of these points, we are designing a satellite called Daksha. Now, Daksha is a proposed Indian satellite mission, still proposed to ISRO, the Indian Space Research Organization, and it is led by IIT Bombay with partner institutes at PRL Ahmedabad, TIFR Mumbai, IUCA Pune, RRI Bangalore, and we have a lot of different uh, folks, astronomers all over the country who are working with us on this particular project, which, when launched, will be the world leader in all of the science cases that it will be able to do. So, not just the electromagnetic counterparts that I talked about, the GRBs that I talked about, it will be also be able to detect these exotic objects like the fast radio bursts. If folks have heard about it, then you have solar flares, you have novae, you have you have lightning on Earth that Daksha will be able to detect, and pulsars, the X-ray pulsars that are out there. Even Daksha will be able to detect that, um, and all of this, while being the best in the world, is what we have shown using our uh, using several calculations that we have published in several journals. In fact, if you have heard of these two satellites called Fermi and Swift, so Fermi and Swift are these X-ray satellites similar to AstroSat, CZTI. that are launched by NASA and ESA. You can find out more about them by Googling them up. But these are the primary two satellites that are detecting these violent explosions out there in space. These are the ones that have been detecting all of the GRBs, majority of the GRBs out there. When Daksha launches, in terms of the volume of the universe that we will be able to probe, we aren't just talking about the distances. We are talking about the volume, because you don't know where these GRBs are going to come from. So you can't really associate a particular distance with it. You would want to look everywhere, right? So in terms of the volume that is probed by these missions, Daksha will be able to do almost 13 times better than this one satellite called Swift. Now, Swift, launched by NASA, Swift's PI is on the paper that we have published, where we have shown these calculations, and all of that information is on our website, dakshasat.in. If you can Google up any of this, you will be able to find it immediately. And all of the relevant information that I just spoke about, all of that is on that website, including our socials and so on, how to get in touch with us. But Daksha in itself, we have shown through different different science cases. In fact, if you have heard of primordial black holes, that is one of the cool things that we recently found out, that it is also possible to detect using Daksha. There are certain inferences that you can make for primordial black holes using the two Dakshas that we'll be able to launch. So that is all about Daksha. Daksha is a twin satellite that we plan to launch with the help of ISRO, which will be a low Earth orbit satellite at 650-kilometer orbit, 6 degrees inclination, similar to astrosat, and it will be a primary transient hunting space telescope, which will be the world's most sensitive X-ray space telescope, which is hunting for transients.
Thank you for providing such a detailed comparison between Daksha Sat and other traditional X-ray space telescopes. It's fascinating to learn about the advantages that Daksha Sat offers in terms of observation capabilities. Now, let's dive deeper into your role as a mechanical engineer in building Daksha Sat. Could you shed some light on your duties and responsibilities? What specific tasks did you undertake or going to undertake in construction and development of Daksha Sat?
Thank you for bringing it up, by the way. For some context, I did my mechanical engineering bachelor's before joining Daksha mission, and as a part of my thesis, I am working on both the mechanical subsystem of Daksha, as well as studying about neutron star mergers and black holes using astrosat. So as a part of my work that I'm doing on Daksha in terms of the mechanical subsystem, what we have to do is that there are a lot of space constraints that you have. So by space constraints, I am not talking about the physical. I'm not just talking about the physical space constraint. I'm talking about the constraints that you see when you go in space. So there are a lot of challenges that you have to overcome in order to launch a satellite, and also to make it function in space. For context, when I said a while back, few seconds back, that we are going to be doing 13 times better than a NASA mission, what does that entail is that we are going to use a lot of detectors on board, almost 10 times more than what we have in astrosat. What does that mean, though, is that we will have a lot of onboard heat going on, which we need to dissipate immediately. So as a part of the mechanical subsystem, what we do is we design thermal control systems through which we are able to dissipate this heat that is generated at the detectors, all the 700 detectors that we will be having on board Daksha. and we will be taking it to a radiator plate and dumping it to space. Not just that, because of the high surface area of Daksha, we will be having a lot of heat coming from sun as well as earth, that will be incident on Daksha that we need to radiate away. So as a part of this team, what we do is we do a lot of simulations where we design different thermal, active, passive thermal control systems, um, which are used to take away and dissipate heat away from the detectors in order for the electronics and the detectors to function in an optimal fashion. Now that is one part of it. The other part of it is uh, are the challenges when you actually launch the satellite. So when you are launching the satellite using any launch vehicle, what you actually are doing are you're subjecting your satellite to a lot of intense vibrations, a lot of intense g forces. So your satellite needs to sustain and endure the very rigorous launch phase of your satellite. What in practice this means is that all of your satellite needs to bear its own weight, and by weight I mean the weight that it will experience at those high g's. And not just that, when the rocket is being launched, it is going to undergo a lot of vibration. So the if I don't know if a lot of folks here must have seen that particular video where a bridge uh, collapsed several decades back because its resonance frequency was matching with the resonance frequency of the wind that was blowing on that day. Um, Similar thing can happen and actually happens everywhere else as well. If your resonance frequency of the component that you're designing is matching the vibration frequency uh, of your rocket, then the vibrations amplify drastically, and that leads to a lot of catastrophic breaking of your components that you are building. So we have to design all of our components in order to increase your fundamental frequency so that it does not match your rocket's vibration frequency. This is what we have to do. It is easier said than done because you are also working against space constraints, the physical space constraints, as well as the weight constraints that you have. But this is a very standard problem that every other satellite has to face, and we have already shown baseline feasibility of all of our components on board our satellite through these simulations, testing, manufacturing, and so on. So what we have done is uh, we have set up everything that we can at this stage, and we have shown the feasibility of actually launching this mission.
Oh, that's amazing. So, like, will there be a constellation of Daksha satellite, or like it's only a one satellite, or
No,
like
so
is there any?
sorry, finish your question, please. Yeah.
So, like in future, are you planning to set up a constellation, or like there will be only one satellite?
So that's a great question. We tried to answer the same using some of the simulations that I did as a part of my research back in my third year of my bachelor's. Uh, so what do you gain out of making a constellation, and what do you lose out on by not making a constellation? So right now the plan is what we want Daksha to be. It will be a twin satellite system. So it will have two satellites diametrically opposite to each other uh, in the low Earth orbit, like I said a while back. Uh, and using this, we will be able to cover 85% of the sky. Now, what does 85% here mean? We will be almost all sky at all times. But going from one satellite, which will cover 50% of the sky, rather even less than 50%, um, we went from 50% to 85% by adding one more satellite. But by adding the third satellite to the constellation, we will be able to gain just 15% of the sky. So adding more satellites to this particular system or the constellation, as you are calling it, the marginal utility of your increasing satellites just decreases as you go on. So, which is why we are focusing on launching 2 satellites, which is going to get us 85% of all sky coverage, uh, which is sufficient to detect almost uh, twice the number of GRBs that are being detected every day out there. And that is, in my opinion, just fantastic in terms of the population studies that we will be able to do using Daksha and so on. So satellite satellite configurations, uh, we are not as such planning to launch more than 2. Right now, the plan is to just launch 2, and 2 is going to give us enough science that that we were not able to do even think of before. Yeah.
Thank you for answering this. Now, there's one more question from audience. What are some advanced electronics and power challenges and requirements for Daksha Sat required to do primordial black hole detection, as it need to scan large epoch volume in universe?
I'm sorry. Can you repeat that question? I missed the second part of it.
So, what are some advanced electronics and power challenges and requirements for Daksha Sat required to do primordial black hole detection, as it need to scan large epoch volume in the universe? This
All
question is more focused towards electronics part, but okay, if you want to answer, you can.
Yeah, so there are probably there are 2 parts of this question. Let me answer the first part, uh, first bit first, which is that the question focused on primordial black holes. These primordial black holes are the oldest black holes that are out there in the universe, and we won't be able to detect them. Uh, we will be able to infer certain properties of these black holes using again GRB detections or transient detections of both the satellites on both the satellites. So there are different timing because of the different timing accuracy of this transient detection on Daksha, we will be able to infer certain properties of these primordial black holes. There's a fantastic paper led by a team at IUCA working with the PI of the mission that was published just a couple of months back, which is talking about the same. If you go to Daksha's website, all the socials, you will be able to find it there. But all of that talks about how primordial black holes we will be able to study more about them using Daksha. Now, let me answer the first part, which was slightly unrelated to primordial black holes, because primordial black holes is one of the 10 different science cases that we have, and electronics on board don't really know what kind of science we are doing there. Electronics on board is just meant to get us the data. Uh, Focusing on that part of the question that asked me about the power requirements. So as the question rightly alludes to, the because of the large number of detectors on board Daksha, we will be having a large power requirement, and this is something that we are hoping to get using big solar panels, which is something that is already done by ISRO in their previous missions. So this power that we are going to need is going to be comparable to previous missions that have been launched. So it is not something that is unheard of, but definitely something that is challenging. And in terms of the electronics, we are currently in the process of designing electronics. So in fact, there are several students who are working with us with Varun at IIT Bombay and at our partner institutes, who are designing and developing all of these electronics as we speak. For example, some of the simulations and testings are going on right now. All of these are meant to space proof your electronics out there, so that it works well in space. For example, there are several challenges out there. I won't have the time, and this is not the correct platform to speak about all of the challenges, because I would rather have some slides to show you what we are talking about instead of just you listening about it. So I'll talk about one rather trivially sounding challenge, but it is something that is very difficult to achieve. Is that when you are talking about Daksha, we always talk about astrosat as one of the pioneer missions that is out there, and CZTI is one of the payloads on board. This detector, CZTI, had 16 uh, detectors on one of the detector board. In order to go from 16 detectors to 20 detectors in a single electronics board, uh, you will have, which is what we are going to have in Daksha. There are enormous challenges that are out there. We are going to be at not just, so the timing accuracy of astrosat was 20 microseconds, and what we are planning to go at is order of a microsecond. So improving your timing accuracy means that you will have 20 times the amount of data that is flowing in from almost 10 times the amount of detectors, and storing all of that data on board, processing all of that data on board, at least some part of it, in order to send out low latency real time alerts to the astronomy community, is something that is a very big task, and we have teams working on it right now. And there are several other challenges I can uh, uh, if we had more time, I would have loved to talk more about it. Uh, but uh, but yeah, that's your brief insight into different electronics that are being built for Daksha.
Thank you for providing these answers. Like we can have Gmeet in future maybe to discuss all these challenges. But okay, like that's a whole different story. We will plan out someday. So now, like, what is its current status and which launch vehicle you are going to use?
Right. So as I was alluding to in the in my previous answer, the current status of Daksha is that we have been continuously working nonstop for the past several years to establish a baseline mission design, and it is complete now. So we have shown that the mission is feasible using the expertise that we have from the various partner institutes, and even within IIT Bombay, we not just have physics department involved. We have mechanical department, electrical department, aerospace department. We have had several PhD students across India working on Daksha. We have had several master's students as well as undergraduate students working on Daksha. Recently, we just tabulated some of these details, and there's almost close to above 50 students who have worked with us uh, on this mission, including myself. I'm still a student now. So baseline mission design is something that is complete for Daksha, thanks to the hard work over this past several years from all of our team members. And apart from that, we have also shown a lot of laboratory models. We have shown that we have demonstrated them to be working as per the mission requirement. We have done some limited amount of testing, which is the mechanical testing, vibration testing. We have manufactured some of the elements for doing this testing. And recently, ISRO has set up a study team for full mission evaluation, and it is a proposed mission to ISRO, and we are hoping for a full approval very soon. But once we get the approval to delivery time scale is going to be very small when you compare it with the median time scales of delivery out there. So we are hoping to get it delivered after approval within 3 years, and that is the kind of hope that we have in future. But on talking about the launch vehicle, those are the details that we will be able to discuss only when we get to an advanced stage of discussions. That those details will be worked out in the future. Um, all we can say is that we are just keeping our fingers crossed, and we are hoping to get the full approval and details like these from ISRO very soon.
Thank you for providing such a valuable insights into your role in building Daksha Sat and progress of the project. It's truly fascinating to hear about the intricate process involved in developing a satellite for space exploration. So now, Gaurav, could you please enlighten us on your role in LIGO and what specific contribution have you made to the project, and like how does your involvement in LIGO complement your work in space exploration?
So Daksha rightly is one of the missions that is going to complement perfectly well with the future activities of LIGO. Uh, so that brings us nicely into LIGO discussions as well. So LIGO is this gravitational wave detector that is functioning operational in the United States of America. It is two detectors in Hanford and Livingston. Both of them are these 4 kilometer long arms that have lasers flowing through it. And when you have gravitational waves passing through these arms, they literally change the amount of length that you have between the two arms, and through that you can cause certain interference at the center of this L-shaped detector, and through that we are able to detect these gravitational waves. So that is what a LIGO detector, LIGO gravitational wave detector is. Uh, as a part of the LIGO science collaboration, I am a part of the team that sends out these gravitational wave merger signal alerts to the astronomy community. In my previous discussions at the start of our entire discussion today, I mentioned that the GRBs that are launched post merger of these neutron stars are launched within a couple of seconds of these merger happening. When you have a GRB that is out there, and after that the afterglow and all of the related phenomena happen, they all fade out very quickly. And in order for the astronomy community with their big telescopes out there, in order for them to detect these uh, afterglows and GRBs, it is very important for LIGO to send out these gravitational wave alerts as soon as they get them. So I'm a part of the team that uh, takes the gravitational wave alerts that are processed by different pipelines that are working and trying to detect these gravitational wave signals, and we take them and inform the community about these alerts. And along with that, we have been recently been working on several new endeavors where we are taking the GRB alerts that are out there, and we are trying to combine them with the gravitational wave alerts right uh, right during the processing stage. And if there's a GRB alert that is going off alongside a gravitational wave alert, then we will be then there are new pipelines that are coming up uh, and online already that are going to be working together hand in hand. So all of this is something that I'm working as a part of the LIGO science collaboration, and there are exciting new things that are going to come up very soon. Uh, I'm sure all of you must have heard about the approval that was given last year by Government of India to for the construction and setup of LIGO India. It was given by the Department of Science and Technology and the Department of Atomic Energy. Uh, it is being set up right here in India in the district of Hingoli in Maharashtra, and it is one of the mega science contributions by Indian astronomy community. Uh, and I'm personally very excited about it in the future.
That's amazing. So, like now moving on to our audience curiosity about LIGO India. Could you provide us with the current update on the project and like what are the processes and development happening in the backend of LIGO India?
Right. So I could not control my enthusiasm in the previous question. So I'm happy that people are asking questions about LIGO India themselves. So LIGO India, like I said, approved last year, and it has three few core institutes called IPR, RRCAT, and IUCA. You can look them up online. Uh, right now, all these core institutes, along with several other folks from different institutes of India, they are working to set up LIGO India as soon as possible. Uh, and there's a lot of background studies. There's a lot of hardware development, science development, software development that needs to be done for the setup of such a giant facility. Right now, in terms of the site, uh, we are studying how the weather at the site is, because these detectors that I talked about, the gravitational wave detectors, these are so sensitive uh, that they are able to detect earthquakes that are going off across the globe. Recently, we had an earthquake that was out there in Japan, but our gravitational wave detectors in US caught it. Um, it is so these gravitational wave detectors are so sensitive. So talking about earthquakes, we are doing also, like the team is also doing carrying out a lot of seismic studies of the site, and along with that there has been some recent development in the constructions actually at the site as well. But uh, in my previous answer I mentioned that the arm length of these LIGO detectors is going to be 4 kilometers, right? So it is not very easy to directly build a 4-kilometer arm length LIGO detector, or any gravitational wave detector for that matter. You need to go in steps. So the currently the team is focusing on building certain prototypes that will be able to mimic the kind of uh, uh, application of the 4-kilometer uh, primary LIGO detector. And through these prototypes, we'll be able to demonstrate all of the different challenges that are out there. For example, you need very powerful lasers in order for you to see these interference pattern. And when you're talking about um, these uh, lasers, you also need very powerful vacuum that will be present in the tubes, the 4-kilometer long tubes. And when you have laser lights, it will be reflected off from giant mirrors. These giant mirrors are suspended from the ground, and these are suspended in order to isolate them from the seismic activities out there. So all of these particular each of these points are major topics of study for the entire team, and there have been uh, huge progresses and leaps that are being carried out by the team, um, by these core institutes primarily, but also by several other like people out there. All of these are part of most of these are a part of the LIGO India Science Collaboration, the LISC as we call it. And in the future, we are they are planning to uh, just scale it as we go. And there are going to be lots of exciting opportunities for everyone to contribute to these big activities at all of these core institutes, as well as at the actual site. Uh, and I can just say that this is going to be something that is going to keep the astronomers busy for the next several years for it to get constructed, and after that for several uh, uh, long years after that as well for the from the science that comes out of it. Uh, LIGO India, it is how is it going to be useful when you talk about that in terms of the actual science that is being done. If you have two detectors, LIGO detectors already functioning, what is the use of LIGO India is what is usually a question that we get. Using LIGO India, the kind of pinpointing of the source you will be able to do is going to be enormously huge change from the currently shared localizations out there. So what do I mean by all of this? What I just said is that currently LIGO, when it detects a gravitational wave signal, it is not able to tell you where exactly the signal came from, because these are based on laser interferometry. They are sensitive to all parts of the sky, but because of the time delays of the signal arriving at different parts at different detectors, since you have two detectors, you will be able to sort of uh, pinpoint and roughly point to the patch of the sky which can contain this particular source which is emitting these gravitational waves. But when you have third detector which is on the other side of the Earth, you can imagine that the baseline between all of these three detectors is going to be huge. So you will be able to distinguish, first you will be able to distinguish noise from actual signal, and also because of the long time delays, you will be able to accurately pinpoint where exactly these gravitational wave merger signals are coming from. And this is going to be a game changer for astronomers like me and for others who also look for these electromagnetic counterparts, right? If you know where to look at, you will be able to point your extremely sensitive telescopes towards that patch of the sky. But if you don't know where to look at, you won't be able to look for those exotic objects. So addition of LIGO India is going to be a game changer in not just gravitational wave science field, but also in terms of the gamma ray bursts, the electromagnetic counterparts, and a lot of extreme other uh, science that we will be able to do. For example, even the tests of general relativity is something that you will be able to probe much better using more number of detections that are expected when the third LIGO detector, which is the LIGO India, comes up online. So that is all about LIGO India, its use, its current status, and all of the activities that are going on as a part of the big science project.
Thank you, sir, for sharing update on LIGO India. Like it truly fascinated me to like it truly motivated me to learn more about all this stuff, LIGO India, and like actually get into this field. We have one question from audience, which is related to Daksha Sat. So the question is, sir, due to the limited historical data on GRB polarization and the complex nature of polarized signals in astrophysical events, what strategies we need to take for Daksha to ensure reliability and accuracy of its polarization measurements?
That's a fantastic question. I might as well add, um, and that is one of the biggest science cases for Daksha. Um, as the question correctly pointed to, that it mentioned a word called polarization. What is this polarization? I'll just quickly tell everyone who is listening. Uh, Polarization is the rotation of light that you have when it passes through a particular patch of the universe. It causes the light different. It causes the light to bend in a certain way, and that is what we can measure when the light photon comes and arrives onto our Daksha detector or any other X-ray detector for that matter. Now, the person who has asked this question rightly pointed out that the amount of information that you have in terms of the polarization study is something that is very limited. In fact, it was limited till Astrosat came online, and Astrosat was one of the first missions who detected polarization and measured polarization rather very accurately from this nearby pulsar called the Crab pulsar. Uh, it is it has over the past several years shown and detected polarization from several gamma ray bursts, and it was able to do that because of a certain configuration that was exploited by the team that built it later. And there were fantastic pipelines and studies that were done by the, again, fantastic core group of the Astrosat CZTI team, which has allowed Astrosat CZTI to be one of the very few missions, if I'm not wrong, one of the 2-3 missions out there that can measure polarization to the accuracy that it can. Um, and in Daksha, we are planning to build upon that legacy even more. We are planning to have even more number of detectors on board and using better time resolution. Like I had pointed out in one of my previous answers to a question, we are going to have a lot better timing resolution. So that is going to allow us to do a lot more polarization studies. And not just that, because of our higher sensitivities, we will be able to do this polarization studies for even fainter GRBs that Astrosat probably wouldn't have been able to do. Not just that, um, the fact that Daksha is an all-sky detector, like I was pointing out again, Astrosat can only do polarization till a particular fraction of the sky, because the gamma ray burst needs to be bright enough, and it needs to align in a particular way that is optimal for the satellite to detect it. Now, for Daksha, because we will be having almost 17 identical surfaces that are looking across the across or at the sky at all times, we will be able to do this for a lot more bursts. So, in terms of polarization of these bright transients out there, Daksha is going to be again a game changer in our books, and it is going to be the field of polarization is going to be exciting when Daksha comes up online.
Really happy to hear that. We will take one last question. So this question is: Hingoli was recently hit by an earthquake. How will it affect the project? He's talking about LIGO.
Yeah, so he is talking. Atharva's question is that, right? So Atharva, I personally did not know that Hingoli was recently hit by a earthquake, but so I can't really comment whether it has caused any issues to the site out there. But since our setup is not yet there at the site, it is not going to cause anything to the setup as such. It But the good news is that earthquakes like these, if it happened, is going to allow us to do a lot. It is going to allow us to study these seismic activities at the site, and earthquakes happening at these sites is not something that is going to cause issues to the issues to the actual detector when it comes online. For example, earthquakes go off all the time in the Pacific Ocean and in the United States where the two LIGO detectors are online. So during the time of the earthquake, your system identifies that there's an earthquake that is going off, and you carry out certain steps in order to just restrict the damage, if at all there is going to be any sort of damage to the system. So there have been that's the advantage of building a LIGO detector in India, is that you have a lot of technical know-how that is already existing in the United States about these detectors, and we are going to build on that foundation that is already cemented out there in US. It took them several decades to make that particular detector over there. We are going to try to make it in much lesser time span than that. Um, so yeah, thanks for informing. By the way, I did not know that Ingoli's earthquake was a recent thing. I will try to find it out more.
Thank you for providing us with a glimpse into the boundless realm of space exploration, showcasing the remarkable advancement and discoveries that shape our understanding of the universe. I want to express my deepest gratitude to both of you for sharing their expertise, passion, and insight with us today. It's been an honor and privilege to host such a distinguished guest, and I'm sure that their words will continue to inspire and resonate with our audience for days to come. Thank you once again to both of you for truly enlightening and enriching event. We look forward to witnessing your continued contribution to the world of science and exploration. Uh, Moreover, thank you for all the people for joining our XSpace. Today there was some technical issues, but we are hoping to not make it again in near future. So thank you for joining. Thank you, Gaurav, for sharing your insights.
Thank you, Parth, and the team for organizing this. And it was a pleasure personally to speak to all of you and for the wonderful questions that were asked, covering all of the science and research activities that I am personally doing. So this was truly a great experience for me as well. If you are wanting to contribute to any of the science that I am talking about, any of the hardware development, any of the activities that you are interested in, first of all just find out about all of these activities by going to different, just googling the different kinds of missions that you are interested in, be it astrosat, LIGO India, or Daksha. uh, all of these projects need a lot of people for them to be achievable and to actually deliver on their science. We are not a we are not a big team. We need as many hands as we can get. So if you are interested in any of this, just follow the social media pages of Daksha or LIGO India. uh, or if you are just wanting to know more, reach out to any of us. We will be happy to guide you further on any of these activities. There are a lot of core institutes working in LIGO India, Daksha, who will be really happy to have students as well as people who are wanting to dedicate a lot of their time to this, to explore astronomy, engineering, and how both of these fields overlap in order to make and give the astronomers fantastic science. So yeah, thank you so much, Parth, and the team at Zeta Gravit. Thank you so much for inviting me.
Thank you. And like I'm sure, like there will be someone who will reach out to you and will be part of LIGO India community or maybe Daksha Sat community. So thank you once again for your time to everyone. This is Attack David signing off.